close your eyes and let yourself drift upward, away from the concerns of the day, up through the atmosphere and into the vast, gentle darkness of space. We're going to take a journey together tonight, a slow, peaceful voyage through the realm of stars, those ancient beacons that have watched over Earth since long before any of us were born. Let's begin with something wonderfully simple. The light touching your eyelids right now, if you were outside on a clear night, has been traveling for years just to reach you. The nearest star to our Sun, a red dwarf called Proxima Centauri, is so far away that its light takes just over 4 years to arrive here. 4 years. That means the gentle glow you might see from that distant point isn't showing you the star as it is now, but as it was 4 years ago. You're looking into the past, witnessing a moment that has already slipped away into time. And this is true of every star you've ever seen. When you gaze up at the night sky, you're not just looking at space, you're looking through time itself. Some of those pinpricks of light began their journey toward your eyes when your grandparents were young, or when ancient civilizations were just learning to write, or even before humans walked the earth at all. The stars are cosmic time capsules, each one carrying news from the past. Now, breathe deeply and picture the sun, our own star, warm and familiar. It seems so constant, so unchanging, but it's actually been burning for about 4.6 billion years. That's nearly a third of the age of the universe itself. And here's something beautifully reassuring: the sun is only about halfway through its life. It has another 5 billion years or so before it begins to change in any dramatic way. 5 billion years of steady, reliable light. All the sunrises and sunsets you've ever witnessed, all the warmth you've felt on a summer day, is part of an immensely long and stable story that will continue far, far into the future. But the sun, as magnificent as it is actually quite ordinary in the grand cosmic scheme. It's what astronomers call a yellow dwarf star, medium-sized, middle-aged, burning at a comfortable temperature. And this ordinariness is part of what makes our existence possible. The sun is neither too hot nor too cool, neither too large nor too small. It's a Goldilocks star, just right for nurturing life on a small blue planet orbiting nearby. Stars come in such a beautiful variety of sizes and colors, like flowers in an infinite garden. The largest stars we know of are the red supergiants, so enormous that if you placed one where our sun is, it would swallow Mercury, Venus, Earth, and Mars. Its surface would extend nearly to Jupiter's orbit. Imagine that, a single star so vast that our entire inner solar system could fit inside it. And yet, despite their tremendous size, these giant stars are actually quite cool compared to smaller stars, glowing with a soft, reddish light that seems almost gentle despite their enormity. Let yourself relax into these vast scales, these enormous stretches of time and space. There's something deeply calming about contemplating the stars. They remind us that we're part of something ancient and ongoing, something much larger than our daily worries. The stars were here long before us, and they'll shine long after we're gone, patient and constant in the darkness. Rest now, and let the starlight from across the ages wash over you, each photon a tiny messenger from the deep past, traveling unimaginable distances just to brush against your world. As you float here in your mind's eye, suspended in the peaceful darkness, let's drift a little deeper into the nature of these celestial companions. You might wonder what stars are actually made of, these glowing spheres scattered across the night. The answer is surprisingly simple, almost poetic in its elegance. Stars are made mostly of hydrogen, the lightest and most abundant element in the universe. In fact, about 73% of a typical star's mass is hydrogen, with most of the rest being helium. These are the same elements that were forged in the very first moments after the Big Bang, the primordial building blocks of everything. Inside every star, including our Sun, something miraculous is happening, a process so powerful and yet so controlled that it has continued for billions of years without pause. Deep in the core, where temperatures reach about 15 million degrees Celsius, hydrogen atoms are being fused together to create helium. This is nuclear fusion, and it's the source of all starlight. Every ray of sunshine that has ever warmed your face, every twinkle you've ever seen in the night sky, comes from this ancient cosmic alchemy, hydrogen transforming into helium, matter converting into pure energy, light, and heat. And the amount of energy is staggering, though it unfolds so steadily it seems almost gentle. Our Sun converts about 600 million tons of hydrogen into helium every single second. 600 million tons. Every second. And yet, the Sun is so massive, so incomprehensibly large, that it can continue this process for those billions of years we mentioned earlier, burning through its fuel at this tremendous rate without running out. There's something oddly comforting about this extravagance, this abundance that powers our world without ever seeming to diminish. Let your breathing slow as we consider how this energy reaches us. When light is created in the Sun's core through fusion, it doesn't immediately escape into space. Instead, it begins a long, wandering journey outward, bouncing and scattering off countless atoms in the dense stellar interior. A single photon, a particle of light, can take between 100,000 and 200,000 years to travel from the core of the Sun to its surface, even though the core and surface are only about 432,000 miles apart. It's an impossibly slow journey through an impossibly dense crowd. But once that photon finally breaks free from the Sun's surface, it takes just 8 minutes and 20 seconds to cross the 93 million miles to Earth. Think about that for a moment, the light touching a leaf, powering a tree, warming the ocean, or falling on your skin right now spent longer than all of recorded human history just trying to escape from the inside of the Sun, and then raced across space in the time it takes to have breakfast. Every sunbeam is ancient and newborn all at once, a traveler from the deep past arriving in the present moment. Now picture the night sky again, that vast tapestry of lights. With your naked eye on a perfectly dark, clear night, far from any city lights, you can see approximately 2,500 stars at any given time. If you could see the entire celestial sphere, both hemispheres of the sky, you'd be looking at about 5,000 to 9,000 stars total. It seems like so many, doesn't it? A number too large to count. And yet this visible multitude is just the tiniest fraction of what's really out there. Our galaxy alone, the Milky Way, contains somewhere between 100 and 400 billion stars. Billion. And the observable universe contains more than 200 billion galaxies, each with billions or even trillions of stars of their own. The numbers become almost meaningless at this scale, too large for the mind to truly grasp. But there's a certain peace in that, too, in acknowledging that we're part of something so vast that our individual concerns, our worries and fears, become as small as a grain of sand on an endless beach. You are here, now, connected to all of this, made of elements forged in ancient stars, bathed in light that has traveled across space and time to find you. Breathe in slowly, breathe out slowly, and feel yourself cradled in this immensity, held gently in the quiet spaces between the stars. Let yourself sink deeper into this peaceful state, your body heavy and relaxed, your mind drifting like a leaf on a gentle stream. We've talked about how stars shine, how they burn their fuel so steadily across the eons. But stars, like all things, are born. And their births are events of breathtaking beauty. Stars are born in nebulae, vast clouds of gas and dust scattered throughout the galaxy. These stellar nurseries can be hundreds of light years across, regions of space so enormous that our entire solar system would be lost in them like a pebble in an ocean. Within these clouds, gravity slowly pulls matter together. A slight density here, a small clump there, and gradually, over hundreds of thousands of years, these regions begin to collapse inward. The cloud fragments into smaller pieces, each one gathering more and more material, growing denser and denser, and as they do, they begin to heat up. Picture this happening in the quiet darkness, a swirling disk of gas and dust, spinning slowly, contracting, warming. When the center of this collapsing cloud reaches about 10 million degrees Celsius, something magical happens. Nuclear fusion ignites. Hydrogen atoms begin to fuse into helium, energy floods outward, and a new star is born, pushing back against gravity's inward pull. This moment, when fusion first begins, marks the birth of a star. It's a transformation from cold, dark matter into a beacon of light that may shine for billions of years. And stars are still being born today, right now, as you rest here. In our Milky Way galaxy alone, approximately 7 new stars are born every single year. 7 might not sound like many, but think of it this way: while you've been alive, hundreds of new stars have flickered into existence, beginning their own long journeys through time. The universe is not a static place, frozen and unchanging. It's alive with creation, constantly renewing itself, bringing new lights into being even as old ones fade. Some of the most famous stellar nurseries are places you might have heard of, the Orion Nebula, for instance, visible even to the naked eye as a fuzzy patch in Orion's sword. This nebula is only about 1,344 light-years away, practically in our cosmic neighborhood, and within it, thousands of stars are forming. Massive young stars illuminate the clouds with ultraviolet light, making the gas glow in shades of red and pink and blue, creating one of the most photographed and beloved objects in the night sky. It's a reminder that creation is still happening, that the story of the cosmos is still being written. Now, let's consider something that might surprise you: not all stars are alone. In fact, most stars exist in binary systems or even larger groups. More than half of all stars have at least one companion star, orbiting around a common center of gravity, bound together by mutual attraction. Imagine 2 suns in the sky, or even 3 or 4, each one contributing its light to a multi-star system. If you lived on a planet in such a system, you might experience multiple sunrises and sunsets in a single day, or periods where the sky never truly darkens because at least one sun is always above the horizon. The nearest star system to us, Alpha Centauri, is actually a triple star system. 2 sun-like stars orbit each other closely, while the third, Proxima Centauri, the one we mentioned earlier, orbits much farther out. These 3 stars have been dancing together for billions of years, their orbits a slow, cosmic waltz played out across distances that dwarf anything we experience in our daily lives. And this companionship is the norm, not the exception. Our sun, solitary and alone, is actually somewhat unusual in having no stellar companions. There's something almost companionable about this knowledge, isn't there? The idea that most stars travel through the cosmos with partners, that even in the vast loneliness of space, there is connection, relationship, and endless orbital embrace. Even the stars, it seems, prefer company to solitude. Rest now in this thought, that you, too, are not alone, that you're connected to others just as the stars are connected to their companions, bound by invisible forces of care and gravity, orbiting through life together in patterns too large and slow to always perceive, but real nonetheless. As you continue to float in this tranquil darkness, your breathing slow and even, let's turn our attention to the colors of stars, those subtle hues that paint the night sky if you look carefully enough. You might think all stars are white, or perhaps a pale yellow, but they actually come in a beautiful spectrum of colors, each one telling us something about that star's temperature and nature. The coolest stars glow red, with surface temperatures around 3,000 degrees Celsius. These red stars burn slowly and steadily, conserving their fuel, living extraordinarily long lives. Then come the orange stars, a bit warmer. Our own sun, that familiar yellow dwarf we've spoken of, has a surface temperature of about 5,500 degrees Celsius, warm enough to appear yellowish-white to our eyes. But the hottest stars of all burn blue and blue-white, with surface temperatures that can exceed 30,000 degrees Celsius or more. It seems almost backwards, doesn't it? In our everyday experience, red means hot, a glowing ember, a burner on a stove. But in the cosmos, red means cool, and blue means blazing. The universe has its own logic, its own rules that sometimes contradict our earthly intuitions. These blue giants, the hottest stars, live fast and die young. They burn through their hydrogen fuel at a furious rate, racing through their life cycles in just a few million years, the blink of an eye in cosmic terms. A massive blue star might consume its fuel thousands of times faster than our sun does, blazing brilliantly but briefly, like a candle that burns at both ends. There's something poignant about this. The brightest stars are often the shortest lived, spending their brilliance quickly rather than conserving it across the eons. Now, let your mind settle on a curious and wonderful fact. Despite being unimaginably hot and bright, stars are actually incredibly inefficient at converting their mass into energy. The sun, for all its power, converts only about 0.7% of the mass involved in fusion reactions into energy. That might sound like a tiny amount, but because of Einstein's famous equation, E equals mc superscript 2, even this small fraction represents an enormous amount of energy. Mass and energy are interchangeable, and even a tiny bit of mass equals a tremendous amount of energy when multiplied by the speed of light squared. This inefficiency is actually a blessing. If stars were more efficient at fusion, they would burn out far too quickly to allow life to develop on planets orbiting them. Let's drift now to consider the sheer diversity of stellar sizes. The smallest stars, called red dwarfs, can be as little as 7.5% the mass of our Sun. These tiny, cool stars are the most common type in the galaxy, outnumbering all other kinds combined. They're faint and difficult to see, invisible to the naked eye even though they're everywhere. But here's what makes them truly remarkable: because they burn their fuel so slowly and efficiently, red dwarfs can live for trillions of years. Trillions. Our universe is only about 13.8 billion years old, which means that not a single red dwarf that has ever formed has yet died of old age. Every red dwarf ever born is still shining somewhere, and will continue to shine long after our sun has exhausted its fuel and faded away. Think about that as you breathe slowly in and out. There are stars out there that will outlive our sun by a factor of 100,000 or more, stars that will still be glowing steadily when our galaxy has changed beyond recognition, when the constellations we know have drifted apart and reformed into entirely new patterns. These small, patient stars are the universe's great survivors, the torches that will keep burning long after everything else has changed. And yet, despite their longevity, we barely notice them. The brightest stars in our night sky, Sirius, Vega, Rigel, Betelgeuse, those are the ones that catch our eye and capture our imagination. But the quiet red dwarfs, the humble majority, are the ones that will inherit the far future, still burning when the universe is ancient beyond our ability to comprehend. There's a gentle lesson in this, perhaps. That brightness and longevity don't always go together. That the quiet, steady, patient presences often endure the longest. That what seems unremarkable can be, in its own way, the most remarkable of all. Let yourself rest in this understanding, your thoughts growing quieter, like those faint red stars barely visible against the darkness, steady and enduring. Your eyelids are growing heavier now, your body sinking deeper into rest, and we continue our slow journey through the stellar realm. Let's turn our attention to something quite magical, the way stars move through space, their hidden motions that unfold too slowly for us to perceive in a single lifetime. From night to night, the stars appear fixed in their positions, forming the same constellations that ancient peoples saw thousands of years ago. But this stillness is an illusion. Every star in the sky is actually moving, racing through space at tremendous speeds. Our own sun, carrying the entire solar system with it, is traveling around the center of the Milky Way galaxy at approximately 828,000 kilometers per hour. That's about 230 kilometers every single second. At this speed, we could circle the Earth's equator in less than 3 minutes. And yet, the galaxy is so vast that even at this incredible velocity, it takes our sun about 225 to 250 million years to complete one full orbit around the galactic center. Picture this. The last time our sun was in this position in its galactic orbit, dinosaurs had not yet appeared on Earth. The time before that, the first complex life was just beginning to emerge in ancient oceans. Our solar system has only completed about 20 orbits since it formed, 20 long circles around the galaxy's heart, each one lasting longer than most species exist. You are, in this very moment, on a cosmic journey that has been unfolding for billions of years, and you're traveling faster than you could ever imagine. You just can't feel it because everything around you is moving together. The stars' motions mean that the constellations we see today are temporary patterns, cosmic coincidences that happen to exist in this particular era. In 50,000 years, the Big Dipper will no longer look like a dipper at all. Its stars will have drifted into entirely new arrangements. The night sky our distant descendants see, if humans are still around, will be subtly different, the patterns shifted and rearranged like pieces on an impossibly slow chessboard. And yet, from night to night, year to year, even lifetime to lifetime, the stars seem eternal and unchanging. We exist in the brief moment between stellar configurations, seeing patterns that feel ancient and permanent but are actually fleeting on cosmic timescales. Now let's consider something that connects the stars to you in the most intimate way possible. The atoms in your body were forged inside stars. Every calcium atom in your bones, every iron atom in your blood, every carbon atom in your DNA, These elements were created by nuclear fusion in the hearts of stars that lived and died before our sun was born. When those ancient stars reached the end of their lives, many of them exploded as supernovae, scattering their enriched material across space. That material eventually became part of the cloud that collapsed to form our solar system, our planet, and ultimately, you. You are made of stardust. This isn't poetic metaphor, it's literal truth. The very substance of your being was cooked in stellar furnaces billions of years ago. You are the universe observing itself, atoms that were once scattered across light years of space now gathered together into the temporary but beautiful pattern that is you. When you look up at the stars, you're looking at distant relatives, the cosmic forges that created the elements that make you possible. The heaviest elements in your body, the gold in a ring you might wear, the iodine in your thyroid, the uranium in the minerals around you, these weren't even created in ordinary stellar fusion. They required the incredible energies of supernovae or the collisions of neutron stars, the most violent events in the cosmos. Every gold atom on Earth, every bit of precious metal, was born in catastrophic stellar death, in explosions so powerful they briefly outshine entire galaxies. And somehow, impossibly, that material found its way here, to this small planet, into the Earth's crust, and eventually into human hands. There's a strange comfort in this knowledge, isn't there? That even in destruction, there is creation. That the deaths of stars scattered the seeds of future worlds, future life. That endings and beginnings are inseparably woven together in the cosmic tapestry. Nothing is ever truly lost, it only transforms, becomes something new, continues the cycle. Rest now, you child of stars, you temporary gathering of ancient light. Let yourself dissolve back into the cosmos for a while, knowing that you are part of something eternal, something vast and beautiful beyond words. Your breathing has found its rhythm now, deep and slow, like waves lapping gently at a distant shore. Let's drift even further into the quieter mysteries of the stars, into the spaces between thoughts, where wonder lives. Consider for a moment the sheer number of stars that have ever existed. Since the universe began 13.8 billion years ago, astronomers estimate that roughly 1% of all the stars that will ever exist have already been born and died. Think about what that means. 99% of all the stars that will ever shine are either burning now or waiting to be born in the vast future ahead. We exist in the early chapters of the universe's story, in what might be called the stellar dawn. The universe is young, still flush with the raw materials for making stars, still energetic and bright. Trillions upon trillions of stars are yet to come, scattered across a future so long it makes our entire history seem like the first moment of a symphony that will play for eons. This means you are witnessing something precious, the universe in its youth, abundant with starlight, rich with possibility. In the unimaginably distant future, when the last stars finally gutter and fade, when the universe grows cold and dark, there will be no one to see what we see now. The night sky filled with stars is a gift of this particular epoch, this brief bright age. Now let your mind settle on something closer to home. The light from stars doesn't just travel to us, it carries information. When starlight passes through a prism or a spectrograph, it separates into a rainbow of colors, but within that rainbow are dark lines, tiny gaps where specific wavelengths are missing. These absorption lines are like fingerprints, telling us exactly which elements are present in a star's atmosphere. By reading these lines, astronomers can determine what a star is made of without ever visiting it, without ever collecting a sample. They can measure stars that are thousands or millions of light years away and know their composition with remarkable precision. This technique revealed something astonishing. Stars throughout the universe are made of the same elements we find on Earth. The hydrogen in a star 10,000 light-years away is identical to the hydrogen in your body. The iron in a distant sun is the same as the iron in Earth's core. The universe, for all its vastness, is made of the same fundamental ingredients everywhere we look. There's something deeply reassuring about this cosmic unity, this universal chemistry that binds everything together. The same spectral analysis also tells us how stars move. When a star is moving toward us, its light shifts slightly toward the blue end of the spectrum, wavelengths compressed by the star's approach, like sound waves bunching up as an ambulance races toward you. When a star moves away, its light shifts toward red, wavelengths stretched by recession. This Doppler shift lets astronomers measure stellar velocities with incredible accuracy, tracking motions of stars across the galaxy, understanding how our cosmic neighborhood is evolving and changing. Most stars, when we measure them this way, are moving at speeds between 20 and 100 kilometers per second relative to us, slower than our sun's orbital speed around the galaxy, but still fast enough to cross a continent in seconds. These motions are gentle drifts in the cosmic ocean, stars following their orbits around the galactic center, pulled by gravity's invisible threads, each one tracing a path through space that will take millions of years to complete. But there are outliers, always outliers. Some stars, called hypervelocity stars, are racing through space at speeds exceeding 1,000 kilometers per second, fast enough to escape the galaxy entirely. These cosmic wanderers, perhaps flung out by close encounters with black holes or ejected from binary systems gone catastrophically wrong, are on one-way journeys into intergalactic space. They'll spend eternity traveling through the void between galaxies, solitary lights in an ocean of darkness, never to return home. There's something both lonely and free about their fate, these stars that broke away from the gravitational embrace of their birth galaxy and struck out into the unknown. Imagine being a planet orbiting such a star, carried away from the galactic disk, watching the Milky Way slowly recede behind you, becoming just another smudge of light against the darkness. Your night sky would grow emptier with each passing million years until finally, you'd be surrounded by almost perfect blackness, with only the distant fuzzy patches of other galaxies to break the dark. A profound isolation, but also a unique perspective, seeing the galaxy from outside, as a whole, as others within it never could. Let these wandering stars carry your last waking thoughts away with them, out into the peaceful darkness, where sleep awaits like a quiet galaxy all its own. You're drifting now, somewhere between waking and sleeping, your mind as quiet as the space between stars. Let's explore something gentle and wondrous, the way stars create the very conditions for worlds like ours to exist. Around many stars, perhaps most, there are planets. For most of human history, we could only wonder if this was true, if Earth was unique or if worlds circled other distant suns. But now we know. The first planet orbiting a sun-like star beyond our solar system was confirmed in 1995, a world called 51 Pegasi b, circling its star every 4 days. Since then, we've discovered thousands upon thousands more. Current estimates suggest that on average, every star in the Milky Way has at least one planet orbiting it. At least one. This means our galaxy alone contains a minimum of 100 billion planets, probably many more. 100 billion worlds, each one a place, a location in space, with its own skies and sunrises, its own geology and weather, its own story. Some of these planets orbit in what astronomers call the habitable zone, that Goldilocks region, not too hot and not too cold, where liquid water could exist on a planet's surface. Water, the universal solvent, the medium in which life as we know it emerges and thrives. Scientists estimate that there could be as many as 40 billion Earth-sized planets orbiting in the habitable zones of Sun-like and red dwarf stars in our galaxy alone. 40 billion potential Earths, 40 billion chances for oceans and atmospheres, for chemistry to become complexity, for complexity to perhaps become life. You are not alone in the universe. Even if life is rare, even if the odds are vanishingly small, with numbers like these, the cosmos must be teeming with worlds where rain falls, where seasons change, where something stirs and grows. And all of this abundance, all these worlds, exist because stars are there, providing warmth and light, creating the stable conditions that worlds need to evolve and endure. The relationship between a star and its planets is an intimate dance. A star's light doesn't just illuminate, it shapes. It drives weather patterns, creates temperature gradients, powers the chemistry of atmospheres. On Earth, starlight falling on ancient seas helped spark the chemical reactions that led to life. Photosynthesis, the process that fills our atmosphere with oxygen and feeds nearly every ecosystem on the planet, is just captured starlight, solar energy transformed into the chemical bonds that power living things. Every tree, every blade of grass, every phytoplankton floating in the ocean is a tiny engine converting starlight into life. And here's something beautiful about stellar variety. Different types of stars create different kinds of worlds. A planet orbiting a red dwarf would receive a deep crimson light, its star appearing perhaps 3 times larger in its sky than our sun appears in ours, glowing like an ember. Plants there, if they existed, might be black or deep purple, evolved to capture the different wavelengths of light their star provides. A planet around a blue giant would bask in intense ultraviolet radiation, its days brilliant and brief. Such stars burn out quickly, giving any worlds around them only a short window to develop before their sun's death. Our own situation, orbiting a stable yellow dwarf, is extraordinarily fortunate. The sun has been remarkably consistent over the billions of years that life has existed on Earth, varying in brightness by less than 0.1% over decades. This stability, this reliability, has allowed life to evolve without catastrophic stellar interruptions, without the star suddenly flaring and sterilizing the planet or dimming and freezing it. Our sun is, in a sense, a good parent, steady, dependable, neither too demanding nor too distant. The distance matters too. Earth orbits at about 150 million kilometers from the Sun, a distance we call 1 astronomical unit, or AU. This distance is almost perfectly calibrated. A little closer, and we'd be Venus, with a runaway greenhouse effect and surface temperatures hot enough to melt lead. A little farther, and we'd be Mars, cold and dry, its water locked in ice or lost to space. We exist in a narrow band where water flows, where temperatures allow complexity, where life can emerge and persist. 150 million kilometers. It seems like such an arbitrary number, and yet it defines everything about our existence. Drift closer, just a bit, and our story never begins. Drift farther, and Earth becomes a frozen wasteland. The universe is full of these precise arrangements, These delicate balances that seem almost intentional, though they're really just the rare combinations that happen to work, selected from countless possibilities. Rest in this thought, that you exist in a place of perfect balance, held at just the right distance from a star of just the right size and temperament, on a world where conditions aligned in just the right way. Unlikely, precious, and yet here you are, breathing softly in the dark, proof that the impossible sometimes happens. You're sinking deeper now, your thoughts becoming wisps of cloud, dissolving into the vastness. Let's turn our attention to the oldest stars, those ancient beacons that have witnessed almost the entire history of the universe. The very oldest stars we've discovered are nearly as old as the universe itself. One star, with the catalog name HD 140283, astronomers sometimes call it the Methuselah star, is estimated to be around 13.5 billion years old, give or take a few 100 million years. The universe itself is 13.8 billion years old, which means this star formed when the cosmos was only about 300 million years old, still in its infancy. This ancient sun has been burning since before our galaxy had fully formed its spiral shape, since before most of the stars we see today were born. It has witnessed the entire story of cosmic evolution, a patient observer floating through space for almost all of time. These ancient stars are different from younger stars like our Sun. They're called population II stars, and they contain very few heavy elements, little carbon, oxygen, or iron. This is because they formed from the nearly pristine material of the early universe, mostly hydrogen and helium with just a trace of lithium. The first stars had no heavy elements at all, because heavy elements didn't exist yet. They had to be created first, forged in the nuclear furnaces of that first generation of stars and then scattered through space when those stars died. The Methuselah star belongs to the second generation, formed from gas that had been only slightly enriched by the deaths of the first stars. When you look at the chemical composition of stars, you're reading their age, their place in the cosmic timeline. Young stars like our Sun are rich in metals. That's what astronomers call everything heavier than hydrogen and helium. These metals come from generations of stars that lived and died, each one adding to the chemical complexity of the universe. Our Sun is a third-generation star at least, made from material that has been recycled through multiple stellar lives. We are latecomers to the cosmic story, beneficiaries of billions of years of stellar alchemy. Now let your mind rest on something curious and subtle. Stars don't shine with perfectly steady light. They pulse and flicker in rhythms too slow or too fast for our eyes to notice. Some stars, called Cepheid variables, brighten and dim with remarkable regularity, periods that can range from a few days to several months. These stellar heartbeats are incredibly useful. There's a direct relationship between how long a Cepheid cycle takes and how bright it actually is. A Cepheid with a longer period is intrinsically more luminous than one with a shorter period. This relationship is like a cosmic measuring stick. If you know how bright a star actually is, and you measure how bright it appears from Earth, you can calculate exactly how far away it must be. Cepheid variables allowed astronomers to measure distances across the galaxy and even to nearby galaxies, revealing for the first time the true scale of the universe. In the 1920s, Edwin Hubble used Cepheid variables to prove that certain fuzzy patches in the sky weren't nebulae within our galaxy at all, but entire separate galaxies millions of light-years away. In a stroke, the universe expanded in human consciousness, growing from one galaxy to billions, from a cosmos measured in thousands of light years to one measured in billions. These pulsating stars beat out their rhythms across the darkness, each one a clock and a lighthouse combined, marking time and distance with their regular variations. Some pulse every few days, brightening and fading with metronomic precision. Others take months to complete a cycle. And all the while, they're helping us map the universe, providing reference points in the void. There are other types of variable stars too, stars that flare suddenly, stars that dim as orbiting companions pass in front of them, stars that erupt in nova explosions and then slowly fade again. The sky is more dynamic than it appears, filled with stars that change on timescales ranging from hours to years. If you could watch the sky in time-lapse across decades, you'd see it shimmer and pulse like a living thing, stars brightening and fading, some winking out entirely, others suddenly appearing where nothing visible was before. Even our sun varies slightly, though we hardly notice. It goes through an 11-year cycle of activity, during which the number of sunspots on its surface waxes and wanes. At solar maximum, the sun is slightly more active, producing more solar flares and ejecting more charged particles into space. At solar minimum, it quiets down, becoming more placid and calm. These cycles have subtle effects on Earth, affecting satellite operations, radio communications, even producing beautiful auroras when solar particles interact with our planet's magnetic field. The sun breathes, in its way, inhaling and exhaling across the years, a slow rhythm underlying the steady light we depend on. Let yourself breathe with these cosmic rhythms, your chest rising and falling like stars pulsing across the night, each breath a tiny echo of the universe's own tempo. Your body is completely relaxed now, heavy and still, while your mind floats free like a mote of dust drifting through a sunbeam. Let's journey to the end of a star's life, to the transformations that await when the fuel finally runs out. When a star like our sun exhausts the hydrogen in its core, billions of years from now, something remarkable happens. The core contracts and heats up, while the outer layers expand outward, swelling to enormous size. The star becomes what astronomers call a red giant, growing so large that if our sun underwent this transformation, it would engulf the orbits of Mercury and Venus, and possibly Earth as well. The star's surface cools as it expands, glowing with that deep red color we associate with cooler stars, but its total luminosity increases dramatically because of its immense size. A red giant can be hundreds of times larger than it was during its main lifetime, a bloated, aging star entering its twilight years. During this red giant phase, something beautiful occurs in the star's core. As temperatures rise to about 100 million degrees Celsius, helium atoms begin to fuse together, creating carbon and oxygen. This helium fusion happens in what's called the triple alpha process, 3 helium nuclei combining in a delicate dance to create a carbon nucleus. This is where the carbon in your body was born, in the cores of dying red giants, created in those desperate final stages when a star seeks new fuel to keep shining. The oxygen you breathe, the carbon that forms the backbone of every organic molecule in your cells, these came from stars in their old age, making new elements as they slowly died. For stars much more massive than our sun, those 8 times the sun's mass or larger, the ending is far more dramatic. These massive stars don't fade gently. When they've exhausted all possible fusion fuel, when their cores have been converted to iron and can fuse no further, the core collapses catastrophically in less than a second. The outer layers of the star then rebound and explode outward in a supernova, an explosion so powerful that for a few weeks, a single dying star can outshine an entire galaxy of billions of stars. Supernovae are among the most energetic events in the universe. In that brief, violet moment, the exploding star releases more energy than our Sun will produce in its entire 10-billion-year lifetime. The explosion is visible across millions of light years, a beacon announcing a star's death to the cosmos. And in that crucible of unimaginable heat and pressure, elements heavier than iron are finally created: gold, silver, platinum, uranium, all the heaviest elements on the periodic table, forged in seconds during the star's final scream of light. In the year 1054, Chinese and Arab astronomers recorded a guest star that appeared in the sky, bright enough to be visible during the day for several weeks. This was a supernova, occurring about 6,500 light-years from Earth. Today, we can see the remnant of that explosion, a beautiful, glowing cloud called the Crab Nebula, still expanding outward from the explosion that created it nearly 1,000 years ago from our perspective. The nebula glows with the energy of the pulsar at its heart, a rapidly spinning neutron star, the compressed core of the original star, now only about 20 kilometers across but containing more mass than our entire Sun. This is one possible fate for a massive star's core, to become a neutron star, an object so dense that a teaspoon of its material would weigh about 1 billion tons on Earth. Neutron stars are made almost entirely of neutrons packed together so tightly that they touch, matter compressed beyond anything we can create or truly comprehend. Some neutron stars spin hundreds of times per second, sweeping beams of radiation across space like cosmic lighthouses. When these beams sweep across Earth, we detect them as pulsars, regular pulses of radio waves arriving with clockwork precision. The fastest spinning pulsar we've discovered rotates 716 times per second. 716 rotations every single second. This is a sphere the size of a city, with more mass than the Sun, spinning so fast that points on its surface are moving at a significant fraction of the speed of light. The precision of pulsar timing is so extraordinary that some pulsars keep time more accurately than the best atomic clocks humans have built. They're the universe's natural timekeepers, the reliable ticking of stellar remnants marking out the seconds across the void. There's something peaceful about the idea of neutron stars, despite their violent births. They're like cosmic monuments, markers of where a star once lived and died. They'll spin for billions of years, slowly losing energy, gradually slowing down but enduring far longer than the stars that created them. In the deep future of the universe, long after the last normal stars have died, neutron stars will still be there, still spinning, still marking time in the darkness. Let yourself slow down now, like a pulsar losing its spin across the eons, your thoughts becoming quieter, your awareness dimming like a star entering its final rest. You're almost dreaming now, balanced on that delicate edge where consciousness fades into sleep. Let's venture into the deepest mysteries, the most enigmatic remnants that stars can leave behind. For the most massive stars of all, even a neutron star isn't the final destination. When a star begins its life with more than about 20 or 25 times the mass of our Sun, its core collapse is so complete, so total, that nothing can stop it. The core compresses past the neutron star stage, past any known form of matter, and continues collapsing until it becomes a black hole, a region of space where gravity is so strong that not even light can escape. Black holes sound frightening, but there's something almost serene about their nature. They're not cosmic vacuum cleaners, hungrily devouring everything around them. They're simply regions where space-time is curved so extremely that anything crossing a certain boundary, called the event horizon, can never return. That boundary for a black hole with the mass of our Sun would be only about 3 kilometers in radius. 3 kilometers. All of the Sun's mass compressed into a sphere smaller than a city, warping space and time around it into something our ordinary intuitions can't grasp. At the center of nearly every large galaxy, including our own Milky Way, there lies a supermassive black hole. These aren't formed from the deaths of individual stars but grew over billions of years, perhaps from smaller black holes that merged, or from massive gas clouds that collapsed in the early universe. The supermassive black hole at the center of our galaxy, called Sagittarius A*, pronounced A star, contains about 4 million times the mass of our Sun. 4 million solar masses, compressed into a region smaller than the orbit of Mercury. And yet, it sits there quietly, 26,000 light-years away from us, at the galactic center, exerting its gravitational influence on the stars that orbit around it. We've actually imaged this black hole, not the black hole itself, which by definition is invisible, but the glowing ring of superheated material swirling around it just before it crosses the event horizon. In 2022, astronomers released the first image of Sagittarius A*, a fuzzy orange ring against blackness, showing us the shadow of the black hole silhouetted against the bright material around it. It took observations from radio telescopes spread across the entire Earth, working together as one planet-sized instrument, to capture this image. We are living in an age where we can photograph the unseeable, where the most mysterious objects in the universe are revealing themselves to us. Despite their mysterious nature, black holes follow simple, elegant rules. A black hole has only 3 properties that matter: its mass, its rotation, and its electric charge. That's it. Everything else about the star that created it, its chemical composition, its history, the complexity of its structure, all of that information is lost. This principle is sometimes called black holes have no hair, meaning they're smooth and featureless, defined by just these 3 numbers. In a way, black holes are the universe's ultimate minimalists, stripped of everything except the most fundamental properties. Around a rotating black hole, and most black holes do rotate, spinning at tremendous speeds, space-time itself is dragged around like water swirling down a drain. This effect is called frame dragging, and it means that near a black hole, there's no way to remain stationary relative to distant stars. Space itself is moving, carrying anything nearby along with it in the black hole's rotation. It's a region where our normal ideas about space and time break down completely, where the fabric of reality itself is twisted into new configurations. The closest known black hole to Earth is about 1,600 light-years away, a comfortable distance, far enough that we're in no danger, but close enough that we've been able to study it. It's a stellar mass black hole, the remnant of a massive star that died long ago, now orbiting with a visible companion star. From Earth, we can watch that companion star wobble as it orbits the invisible black hole, measuring the dance between light and darkness, between what we can see and what remains forever hidden. There's something oddly peaceful about knowing black holes exist. They're the universe's ultimate recyclers, places where matter and energy take on forms we can barely imagine, where the story of a massive star reaches its conclusion in a singularity beyond our comprehension. They're boundaries where our knowledge ends, reminders that the cosmos still holds mysteries we may never fully solve, depths we may never fully plumb. Let yourself sink toward that peaceful boundary now, where thought dissolves, where consciousness crosses its own event horizon into the quiet darkness of sleep. Your breathing is so slow now, so gentle, barely stirring the stillness around you. Let's drift back from those dark depths to something softer, more luminous, the nebulae, those clouds of gas and dust where stars are born and where they return when they die. When a star like our sun finally exhausts its fuel and sheds its outer layers, those layers don't simply vanish. They expand outward as a beautiful, glowing shell of gas called a planetary nebula, though the name is misleading, as these nebulae have nothing to do with planets. Early astronomers through their small telescopes thought these round, fuzzy objects looked like planets, and the name stuck. But what they're actually seeing is a dying star's last breath, its outer atmosphere gently expelled into space, lit from within by the hot, dense core left behind. These planetary nebulae glow in extraordinary colors, reds from hydrogen, greens and blues from oxygen, deep crimsons from nitrogen. They form shapes of stunning complexity, rings, hourglasses, spirals, butterflies. The Cat's Eye Nebula, the Helix Nebula, the Ring Nebula, each one is unique, a celestial artwork created by physics and chemistry, by the interaction of stellar winds and magnetic fields, by the tumbling motion of dying stars. They last for only about 10,000 years before dispersing into space, fading back into the interstellar medium. 10,000 years seems long to us, but in cosmic terms, it's a brief flowering, a moment of beauty before the curtain falls. The central star of a planetary nebula, the exposed core of the original star, is called a white dwarf. This is what our sun will eventually become, about 5 to 7 billion years from now. A white dwarf is roughly the size of Earth but contains about half the mass of the Sun. Imagine compressing half of our Sun's mass into a sphere the size of our planet. The density is staggering. A teaspoon of white dwarf material would weigh about 5 tons. Not as extreme as a neutron star, but still far beyond anything we encounter in everyday life. White dwarfs are supported not by fusion, they've run out of fuel entirely, but by something called electron degeneracy pressure, a quantum mechanical effect where electrons resist being compressed into the same space. This pressure has nothing to do with temperature, it's a fundamental property of matter at extreme densities. A white dwarf can be incredibly hot when it first forms, surface temperatures of 100,000 degrees Celsius or more, but it has no internal heat source, so it simply radiates its stored heat away into space, gradually cooling over billions upon billions of years. The coolest white dwarfs we've observed have temperatures around 3,000 degrees Celsius, still hot by human standards, but cool for a star. These ancient white dwarfs glow a faint red or even dimmer, barely visible ghosts of stars that died long ago. Eventually, after timescales longer than the current age of the universe, a white dwarf will cool completely, becoming a black dwarf, a dark, cold sphere of crystallized carbon and oxygen, the final ember of a star gone completely cold. But the universe isn't old enough yet for any black dwarfs to exist. Every white dwarf ever created is still cooling, still faintly glowing, still carrying a whisper of the heat from its former life. There's something poetic about white dwarfs made of carbon and oxygen, the same elements that make up so much of living things. In a sense, these stellar remnants are like cosmic diamonds, crystalline spheres of carbon floating in space. Some white dwarfs are thought to have cores that have actually crystallized, with carbon atoms arranging themselves into diamond-like structures under the immense pressure. Stars literally become jewels in death, treasures scattered through the galaxy, too faint for most telescopes to see but precious nonetheless. Our own sun's future is written in these white dwarfs we observe. In about 5 billion years, it will swell into a red giant, engulf the inner planets, shed its outer layers into space as a planetary nebula, and then settle into its long twilight as a white dwarf. It will cool slowly over trillions of years, long after the Earth is gone, long after everything we know has turned to dust. But even then, the matter that made up our sun, and the Earth, and us, won't disappear. It will drift through space as part of a nebula, eventually mixing with other clouds, contributing to new generations of stars, new planets, perhaps new life. Nothing is ever truly lost in the cosmos. Everything transforms, everything continues, everything becomes part of something new. The carbon in the air you exhale was once in a star. The oxygen you breathe in was forged in stellar cores. You are participating in a cycle of creation and transformation that has been going on since the first stars formed, and it will continue long after the last stars fade. Rest now in this eternal recycling, this cosmic wheel that turns and turns, making new things from old, turning endings into beginnings. You're barely here now, consciousness like a distant star at the edge of vision, fading in and out. Let's bring our journey full circle, returning to the night sky, to what the stars mean for us, for Earth, for the quiet moment you're in right now. The light from stars doesn't just carry information about the stars themselves, it connects us across time and space to everyone who has ever looked up at the night sky. The Big Dipper, which you might have seen countless times, has been visible in roughly the same shape for thousands of years. The ancient Egyptians saw it. The builders of Stonehenge saw it. Every human civilization has looked up and seen these same patterns, these same lights. When you gaze at the stars, you're participating in the oldest human activity, sharing an experience with every person who has ever lived and wondered about the lights above. The stars have guided us, literally and figuratively, for all of human history. Before GPS, before maps, before compasses, sailors navigated by the stars. The North Star, Polaris, sits almost directly above Earth's North Pole, appearing stationary in the sky while all other stars seem to rotate around it. For centuries, travelers have used Polaris to find their way, to orient themselves when lost. That star sits about 433 light-years away, meaning its light has been traveling since around the year 1590 to reach us now, light that began its journey when Shakespeare was writing his plays, now guiding ships and hikers across Earth's surface. But Polaris hasn't always been the North Star, and it won't be forever. Earth's axis wobbles very slowly over a cycle of about 26,000 years, a phenomenon called axial precession. This means that the point in the sky directly above our North Pole changes over millennia. In ancient Egyptian times, around 2700 BCE, the pole star was a different star called Thuban in the constellation Draco. And in about 12,000 years, the bright star Vega will be our pole star instead. Even the seemingly fixed points in our sky are temporary, part of great cycles unfolding over timescales that dwarf human civilizations. The stars you see depend entirely on where you are on Earth. If you stand at the North Pole, you see the same stars circling overhead every night, never rising or setting, the northern circumpolar stars. If you stand at the equator, you can see stars from both the northern and southern hemispheres over the course of a year, the entire celestial sphere available to you. And if you travel from north to south, you'll see familiar constellations sink toward the horizon while new ones emerge, stars that were invisible from your home now dominating the sky. The cosmos reveals itself differently depending on your vantage point, a reminder that perspective shapes what we see and know. On the clearest, darkest nights, away from all light pollution, the human eye can see stars as faint as magnitude 6 or even 6.5. Magnitude is an ancient system of measuring brightness. The brightest stars are magnitude 1, and each increase in magnitude number represents a star about 2.5 times dimmer. A magnitude 6 star is exactly 100 times fainter than a magnitude 1 star. This system seems backwards, higher numbers meaning dimmer, but it comes from ancient Greek astronomers who ranked stars by importance, with first-ranked stars being the brightest. The system has been refined and extended, but the basic logic remains, a connection to those ancient observers reaching across millennia. In perfect darkness, with eyes fully adapted to the night, you can see not just individual stars but the soft, milky band of light stretching across the sky, the combined glow of millions of stars in the disk of our galaxy, so distant and numerous that they blur together into a luminous river. This is the Milky Way as it appears from within, our home galaxy seen edge-on, a reminder that we're embedded in something vast, one star system among hundreds of billions, looking out from inside at the collective light of our stellar family. Most people alive today have never seen a truly dark sky. Light pollution from cities and towns has erased the Milky Way from view for the majority of humanity. It's estimated that 80% of the world's population now lives under skies so bright that they cannot see our own galaxy. An entire generation is growing up never experiencing what our ancestors took for granted, a sky full of stars, the Milky Way arching overhead, the profound darkness that makes the stars truly visible. But in the remaining dark places, deserts, mountains, remote islands, the ancient sky persists, waiting to remind us of our place in the cosmos. When you close your eyes now, picture that darkness, that deep, soft darkness filled with ancient lights. Picture yourself lying on the ground, looking up, with nothing between you and infinity but the thin veil of atmosphere. Feel the earth solid beneath you, feel yourself held gently on the surface of this spinning planet, this small world orbiting an ordinary star in an ordinary galaxy, and yet, impossibly, miraculously, here you are, aware, conscious, able to contemplate it all. The stars are still there, even when you can't see them. They shine through clouds, through daylight, through the walls around you. Their light is always falling on Earth, always has been, always will be, for as long as stars exist and Earth endures. You are bathed in starlight even now, in this quiet darkness, particles that traveled across space finding you here, in this moment, completing journeys that began years or centuries or millennia ago. Rest now, held in this vast tapestry of light and darkness, knowing you are home, you are safe, you are exactly where you need to be. The stars keep their patient watch while you sleep, and they will still be there when you wake, eternal companions on this brief, beautiful journey through the cosmos. Sleep well, child of Earth and stars. Sleep well. For those still drifting in this twilight space between waking and dreaming, we continue our gentle voyage through the stellar realm. Let your awareness settle softly, like dust falling through a sunbeam, as we explore the invisible forces that bind stars together across the vast emptiness of space. Gravity is the architect of the cosmos, the gentle hand that gathers stars into clusters and clusters into galaxies. Throughout our galaxy, There are groupings of stars born together, still traveling together through space like old companions who refuse to part ways. The nearest of these to us is the Hyades cluster, a loose collection of a few hundred stars in the constellation Taurus, sitting about 153 light-years from Earth. These stars all formed from the same cloud of gas and dust roughly 625 million years ago, ancient by human standards, but relatively young in stellar terms, and they've remained gravitationally bound ever since, drifting through the galaxy as a family. Even more spectacular are the globular clusters, dense, spherical collections of stars that orbit in the halo around our galaxy. These clusters can contain anywhere from tens of thousands to millions of stars, all packed into a region perhaps 100 to 200 light-years across. If you lived on a planet in the core of a globular cluster, your night sky would be astonishing, thousands of stars bright enough to cast shadows, the sky so filled with light that true darkness would never fall. The nearest stars to you might be only a few light-weeks away, not light-years. You could see neighboring star systems with the naked eye as actual disks, not just points of light. The globular clusters around our galaxy are among the oldest structures in the Milky Way, with ages of 10 to 13 billion years. They formed when the galaxy itself was young, and they've orbited through it ever since, following great looping paths that take millions of years to complete. Some pass through the galactic disk, others swing far out into the halo and then return. They're time capsules, preserving stars from the ancient universe, giving us windows into what stellar populations looked like in the cosmos's youth. Now let your thoughts drift to something both familiar and strange, the fact that stars twinkle. You've seen it countless times, stars shimmering and dancing in the night sky, their light wavering and fluctuating. But this twinkling has nothing to do with the stars themselves. Stars are so distant that they appear as perfect points of light, and if you could see them from space, they would shine with absolutely steady illumination. The twinkling happens in Earth's atmosphere, where pockets of air at different temperatures move and shift, bending the starlight slightly this way and that as it passes through. Each twinkle is a reminder that we're looking at the cosmos through a veil, through layers of moving air that separate us from the vacuum beyond. Planets, by contrast, don't twinkle nearly as much, because they appear as tiny disks rather than points of light. The light from different parts of the planetary disk averages out as it passes through the atmosphere's turbulence, creating a steadier glow. This is one way ancient astronomers distinguished planets from stars, the wandering stars that moved against the background of fixed stars, the lights that shone steadily rather than twinkling. Mars, Venus, Jupiter, Saturn, our sibling worlds reflecting our sun's light, they have a calm, unwavering quality that sets them apart. The turbulence that causes twinkling is why astronomers build observatories on high mountains and in dry climates. The less atmosphere between the telescope and space, the steadier the image. The summit of Mauna Kea in Hawaii rises 4,207 meters above sea level, placing it above 40% of Earth's atmosphere and almost all of its water vapor. Here, the stars twinkle less, the sky is darker, and the view is clearer. Some of the world's largest telescopes cluster on this dormant volcano, their domes rising like temples to the night sky, gathering ancient starlight and transforming it into knowledge. Even better than mountaintops is space itself. The Hubble Space Telescope, orbiting Earth above the atmosphere entirely, captures images of stars without any atmospheric distortion, perfect, steady points of light, or in some cases, resolved images showing stellar surfaces and surroundings with unprecedented clarity. Hubble has orbited Earth for more than 3 decades now, at an altitude of about 547 kilometers, circling our planet every 95 minutes, its instruments tirelessly gathering photons from across the cosmos and sending them down to us as data, as images, as revelations. Breathe slowly, steadily, like starlight passing through clear space, undisturbed and pure. Feel yourself rising above the turbulence, above the shimmer and shake of the everyday world, settling into a clearer, calmer realm where everything becomes still. Your mind is quiet now, thoughts arriving and departing like clouds drifting across a moonlit sky. Let's turn our attention to the rhythms of the cosmos, to the way stars and galaxies move in great patterns that unfold across space and time. Our Milky Way galaxy is not alone in the universe, nor does it drift in isolation. It belongs to a small collection of galaxies called the Local Group, a gravitationally bound cluster of more than 50 galaxies spanning about 10 million light-years across. Most of these galaxies are small dwarf galaxies, faint collections of a few billion stars each, satellites orbiting the 2 dominant members of the group, our Milky Way and the Andromeda Galaxy. These 2 spiral galaxies are the giants of our neighborhood, each containing hundreds of billions of stars, each ruling their own retinue of smaller companion galaxies. Andromeda, also known as M31, is the nearest large galaxy to our own, sitting approximately 2.5 million light-years away. On a dark night, away from city lights, you can see it with your naked eye as a small, fuzzy oval in the constellation Andromeda, though what you're seeing is only the bright core, not the galaxy's full extent. When you look at that faint smudge of light, you're seeing the combined glow of roughly 1 trillion stars, a galaxy even larger than our own, and the light you're receiving left that galaxy 2.5 million years ago, when early human ancestors were just beginning to walk upright on the African savanna. But here's something remarkable: Andromeda is moving toward us. While most galaxies in the universe are moving away from each other as space itself expands, Andromeda and the Milky Way are being drawn together by their mutual gravitational attraction. The 2 galaxies are approaching each other at about 110 kilometers per second, roughly 400,000 kilometers per hour. At this speed, you could travel from Earth to the Moon in less than an hour. And yet, because the distance between the galaxies is so vast, they won't collide for approximately 4.5 billion years. When that collision finally happens, it will be a slow-motion dance of unimaginable scale. The 2 galaxies will interpenetrate, their stars passing by each other like fireflies in the night. Despite containing hundreds of billions of stars each, the distances between individual stars are so vast that actual stellar collisions will be extremely rare. Instead, gravity will pull and stretch both galaxies, creating long tidal tails of stars, triggering massive bursts of new star formation as gas clouds collide and compress. Over the course of billions of years, the 2 galaxies will merge completely, forming a single, larger elliptical galaxy that astronomers have already nicknamed Milkomeda. By the time this merger is complete, our Sun will already be approaching the end of its life, beginning its transformation into a red giant. If Earth still exists, and that's uncertain, given the Sun's expansion, the night sky will be transformed, filled with new constellations, new patterns, the Andromeda Galaxy no longer a distant blur but an overwhelming presence, filling half the sky, its spiral arms stretching across the heavens. Of course, no human will be there to see it, but the stars will witness this cosmic dance, this union of galaxies playing out across eons. This collision is part of a larger pattern. Galaxies throughout the universe are constantly interacting, merging, being reshaped by gravity's patient hand. Our own Milky Way bears the scars of ancient collisions, streams of stars in our halo that were once separate dwarf galaxies, now torn apart and absorbed, their stars becoming part of our galaxy's structure. In a sense, the Milky Way is not a single entity but an amalgamation, built up over billions of years from smaller pieces, still growing, still evolving. There's a certain peace in contemplating these vast timescales and enormous distances. The collision with Andromeda sounds catastrophic, but it will unfold so slowly that no single star system will experience it as a sudden event. Stars that are born during the early stages of the merger will live and die before it's complete. The universe operates on timescales that make our concerns dissolve into insignificance, and yet everything we experience, every sunrise, every moment of connection, every breath, happens within this vast cosmic context, temporary but real, fleeting but precious. Let yourself merge with the darkness now. Boundaries dissolving, thoughts blending into the peaceful void. You are part of this great cosmic dance, this slow waltz of matter and energy across space and time, and for now, for this moment, you can simply rest in the stillness between movements. You're deep in the current of sleep now, barely tethered to waking consciousness, drifting in that peaceful space where time loses meaning. Let's float together to the edges of what we know, to the boundaries where starlight fades and mystery deepens. The universe is expanding, carrying galaxies away from each other like boats on a slowly swelling ocean. This expansion was discovered in 1929 by Edwin Hubble, who noticed that nearly all galaxies show a redshift in their light waves stretch toward the red end of the spectrum, indicating motion away from us. The farther away a galaxy is, the faster it appears to be receding. This relationship, now called Hubble's law, revealed something extraordinary. The universe is not static but growing, the space between galaxies increasing with every passing moment. But the expansion isn't uniform throughout all of space. On small scales, within galaxies, within galaxy clusters, gravity holds structures together. Our local group, for instance, isn't expanding, its galaxies are gravitationally bound, orbiting each other, sometimes colliding. It's only on the largest scales, between galaxy clusters and superclusters, that expansion dominates and structures move apart. The current rate of expansion is about 70 kilometers per second per megaparsec, a unit that means for every 3.26 million light-years of distance, objects are receding at an additional 70 kilometers per second. The farther away something is, the faster it's moving away from us, not because the objects themselves are moving through space, but because space itself is expanding between them. This expansion creates a horizon, a limit to what we can see. Light from the most distant galaxies has been traveling toward us for most of the age of the universe, but because space has been expanding while that light travels, those galaxies are now much farther away than the light travel distance would suggest. The observable universe, the sphere of space from which light has had time to reach us, extends about 46.5 billion light-years in every direction, even though the universe is only 13.8 billion years old. The expansion of space has stretched that distance, creating a cosmic horizon beyond which we simply cannot see, no matter how powerful our telescopes. Beyond that horizon, the universe continues, there's no edge, no wall. Just more galaxies, more stars, more space extending in all directions. But their light will never reach us. They exist in a realm forever beyond our observation, separated from us not by physical barriers but by the expansion of space itself and the finite speed of light. In a sense, every observer in the universe is at the center of their own observable sphere, their own horizon, their own limited view of the infinite. And that observable universe contains an almost incomprehensible number of stars. With roughly 200 billion galaxies in the observable universe, each containing on average hundreds of billions of stars, the total number of stars is estimated to be around 200 billion trillion, or 2 times 10 superscript 2 superscript 3. That's a 2 followed by 23 zeros. To put it another way, there are more stars in the universe than grains of sand on all the beaches on Earth. More stars than seconds that have passed since the universe began. More stars than words spoken by every human who has ever lived. Each one of those stars is a sun, potentially with its own family of planets, its own story of birth and life and eventual death. Each one is a nuclear furnace, fusing elements, creating light, warming space around it. Most of those stars have never been seen by human eyes, will never be catalogued or named, will live and die in cosmic anonymity. And yet they exist, scattered across distances so vast that their light will never reach us, burning in regions of space that will remain forever unknown to us, part of a universe far larger than the small bubble we can observe. There's something oddly comforting about this unknowability, this vastness that exceeds all human comprehension. It means the universe is not small or constrained or fully mapped. It means there will always be mystery, always be frontiers beyond our reach, always be wonders we can imagine but never directly witness. We are small, yes, but we are also part of something boundless, something that extends far beyond the limits of our perception or understanding. Rest in this immensity, this darkness filled with distant lights, this expansion that carries everything slowly apart while gravity holds small pockets together. You are here, now, in this moment, in this one small place, and that is enough. The universe continues its slow unfurling whether you observe it or not, and you can simply be, simply rest, simply let go. Sleep is so close now, like a shore you're drifting toward on gentle waves. Let's linger a while longer in the darkness, exploring the quieter mysteries of stars, the subtle phenomena that astronomers have discovered in their patient watching of the night. Not all stars are isolated or paired with companions. Some exist in spectacular environments, surrounded by disks of material left over from their formation. Young stars, still in the process of gathering their final mass, are often wreathed in protoplanetary disks, flat, rotating clouds of gas and dust from which planets eventually form. These disks can extend for billions of kilometers, containing enough material to create dozens of worlds. Our own solar system formed from such a disk about 4.6 billion years ago, the sun igniting at the center while planets coalesced in the surrounding material like pearls forming in an oyster. We've observed these protoplanetary disks around other stars with stunning clarity. The ALMA telescope array in Chile has captured images showing gaps and rings in the disks, clear signs that planets are forming within them, carving out lanes as they orbit and sweep up material. One of the most famous images is of the star HL Tauri, a young star only about 450 light-years away in the constellation Taurus. The disk around it shows multiple dark gaps, evidence of at least 5 planets forming simultaneously, worlds being born even as we watch. The disk extends approximately 90 astronomical units from the star, 90 times the distance from Earth to the Sun, a planetary system still under construction. Watching these disks is like looking into our own past, seeing the process that created our world playing out around other stars. Every planet in our solar system, every moon, every asteroid, all condensed from a disk like these, particles of dust sticking together, growing larger through countless gentle collisions, eventually becoming the worlds we know. The iron core of Earth, the rings of Saturn, the icy surface of Europa, all were once formless dust orbiting a young sun, gradually finding their shapes, their identities, their places in the celestial dance. Some stars show evidence of planets not through direct imaging but through subtle wobbles in their motion. As a planet orbits a star, the star also orbits their common center of mass, a point called the barycenter. If the planet is massive enough, or close enough, this orbital motion causes the star to move in a small circle or ellipse. From Earth, we can detect this motion through the Doppler effect. The star's light shifts slightly bluer when moving toward us, slightly redder when moving away. These periodic shifts reveal the presence of unseen companions, invisible planets betrayed by the gravitational dance they create. The first exoplanet discovered around a Sun-like star, 51 Pegasi b, which we mentioned earlier, was found using exactly this technique. Astronomers detected a wobble in the star 51 Pegasi, repeating every 4.2 days, and calculated that a planet roughly half the mass of Jupiter must be orbiting extremely close to its star. This discovery revolutionized our understanding of planetary systems, revealing that giant planets could exist in tight orbits unlike anything in our solar system, so-called hot Jupiters, gas giants circling their stars in just days, their atmospheres heated to thousands of degrees. Since that discovery, the wobble technique has revealed hundreds of exoplanets, many of them strange and unexpected, planets more massive than Jupiter, planets in eccentric elongated orbits, planets orbiting binary star systems where two suns share the sky. The diversity of worlds is staggering, far exceeding what anyone imagined before we began finding them. Each discovery reminds us that the universe is more creative than our theories, more varied than our predictions, full of possibilities we never anticipated. There's another method too, watching for transits, moments when a planet passes directly in front of its star from our perspective, causing a tiny, brief dimming. The Kepler Space Telescope used this method to discover thousands of exoplanets, staring at a single patch of sky for years, monitoring the brightness of over 150,000 stars simultaneously, detecting the subtle dips that reveal planetary transits. A dip of 1% in brightness might indicate an Earth-sized planet crossing a Sun-like star. These tiny eclipses, lasting hours, repeat with clockwork precision, revealing not just the planet's existence but its size, its orbital period, sometimes even hints about its atmosphere. Let these discoveries wash over you like gentle waves, worlds upon worlds, systems upon systems, an abundance of planets scattered through the galaxy. Every star you've ever seen likely has worlds of its own, places with their own skies, their own landscapes, their own silent stories unfolding in the darkness. You are not alone. Earth is not alone. We are one world among countless others, one small stage among an infinity of stages. Drift now, let consciousness slip away like a planet moving into the shadow of its star, peaceful and gradual, darkness arriving as a blessing, not a threat. You're barely here now, a whisper of awareness in the vastness. For those still listening, still drifting on the edge of dreams, let's explore one of the most beautiful phenomena in all of stellar astronomy, the way stars communicate across the darkness through their light. Stars are not silent. They speak to us constantly through the electromagnetic spectrum, sending messages across space in wavelengths our eyes cannot see. What we perceive as visible light, the rainbow from red to violet, is only a tiny sliver of the full range of radiation stars emit. Some stars shine brightly in infrared, radiating heat we could feel but not see. Others pour out ultraviolet light, invisible to our eyes but detectable by specialized instruments. The hottest, most energetic stellar phenomena emit X-rays and even gamma rays, radiation so energetic it would be lethal up close but arrives at Earth harmlessly weakened by distance. Our Sun emits most of its energy in the visible spectrum, which is not a coincidence. Our eyes evolved to detect the wavelengths most abundant in sunlight. Life on Earth shaped itself around our star's particular output, tuning biological sensors to match the available light. On a planet orbiting a red dwarf, evolution might favor eyes sensitive to infrared. Around a hotter blue star, ultraviolet vision might emerge. The colors we see, the wavelengths we're sensitive to, are not universal but local, adapted to our specific star, our particular cosmic home. When astronomers want to study the universe comprehensively, they must observe in all these wavelengths, building a complete picture from many different types of light. Radio telescopes detect the longest wavelengths, picking up emissions from cold gas clouds, from pulsars, from the remnants of the Big Bang itself. The Very Large Array in New Mexico consists of 27 radio dishes, each 25 meters across, working together to capture radio waves from across the cosmos. These dishes can be spread across a region up to 36 kilometers wide, creating an instrument with the resolving power of a single telescope that size, a technique called interferometry, where many small telescopes combine to act as one enormous eye. Radio astronomy has revealed phenomena invisible to optical telescopes, clouds of hydrogen gas between the stars, the jets of material shooting from black holes, the remnants of ancient supernovae still glowing in radio frequencies long after their visible light has faded. The universe in radio waves looks entirely different from the universe in visible light, less a collection of bright points and more a tapestry of diffuse glows, of structures spanning light years, of emission from regions too cold to shine visibly but still radiating energy into space. At the other end of the spectrum, X-ray telescopes like NASA's Chandra X-ray Observatory observe the hottest phenomena in the universe, gas falling into black holes and heating to millions of degrees, the coronas of stars where temperatures soar far beyond the stellar surface, the shock waves from supernova explosions. X-rays cannot penetrate Earth's atmosphere, so these telescopes must operate in space, orbiting above the protective blanket of air that shields us from harmful radiation but also blocks our view of the high-energy cosmos. Chandra orbits Earth in a highly elliptical path, ranging from about 16,000 kilometers at its closest to 133,000 kilometers at its farthest, nearly a third of the way to the Moon at its most distant point. This orbit takes it above the radiation belts that surround Earth, regions where charged particles trapped by our planet's magnetic field could interfere with sensitive observations. From this vantage, it has observed the universe's most violent events, capturing images of galaxy clusters, stellar corpses, and black holes actively feeding on surrounding matter. Each wavelength tells a different story about the same objects. A supernova remnant might appear as a faint wisp in visible light, a bright ring in radio waves, and a brilliant shell in X-rays, each view revealing different temperatures, different energies, different aspects of the same cosmic event. To understand stars fully, we must see them in all their forms, gather all the messages they send across the electromagnetic spectrum, assemble the complete portrait from many partial views. The universe is richer than any single perspective can capture, more complex than any one wavelength can reveal. This is true of stars, and perhaps true of everything, that reality has many layers, many aspects, that what we see depends on how we choose to look, what instruments we use to gather light from the darkness. Rest now in this multidimensional cosmos, where every object is many things at once, where truth emerges from the synthesis of many observations, many perspectives, many ways of seeing. The boundary between sleep and waking has dissolved entirely now, and yet here you remain, floating in this liminal space. Let's venture into one of the most profound mysteries the stars have revealed, the nature of time itself, and how it changes near massive objects. Einstein showed us that time is not absolute, not the same everywhere and for everyone. Time flows differently depending on how fast you're moving and how deep you are in a gravitational field. Near a massive object like a star, time actually runs slower than it does in the empty space far away. This seems impossible, contradictory to our everyday experience, but it's been measured, confirmed, woven into the very fabric of our GPS satellites, which must account for time dilation or they would give incorrect positions within minutes. Near the surface of our sun, time passes about 66 parts per billion slower than it does here on Earth. That's a tiny difference. Over the course of a year, a clock on the sun's surface would fall behind an Earth clock by only about 2 seconds. But that difference is real, measurable, a testament to gravity's ability to warp not just space but time itself. For more massive objects, the effect becomes dramatic. Near a neutron star, time slows noticeably. Near a black hole, time can slow to a crawl relative to distant observers. Imagine watching something fall toward a black hole from a safe distance. As the object approaches the event horizon, it would appear to slow down, its motion becoming more and more sluggish, the light from it shifting redder and redder as time dilation and gravitational redshift take hold. To the falling object, assuming it could somehow survive the tidal forces, nothing would seem unusual. It would cross the event horizon in finite time from its own perspective. But to you, watching from afar, it would appear to freeze at the horizon, taking infinite time to cross that final boundary, its image growing dimmer and redder until it fades from view entirely. This means that from our perspective, nothing has ever actually fallen into a black hole. Everything that has approached one is still frozen at the horizon, caught in that final moment before crossing, suspended in time. And yet, from the perspective of infalling matter, the crossing happens quickly, inevitably. Both perspectives are valid, both are true within their own reference frames. The universe contains multiple truths, multiple valid experiences of the same events, depending on where you are and how you're moving. Stars themselves experience time differently at their cores than at their surfaces. The core of the sun, where fusion occurs, exists in a slightly slower temporal frame than the surface, where light finally escapes. The photons that struggle for hundreds of thousands of years to work their way from core to surface are navigating not just spatial distance but temporal gradients as well, climbing up through layers where time flows at slightly different rates. This relativistic effect also influences binary star systems, particularly those involving compact objects like white dwarfs or neutron stars. In some exotic binaries, two neutron stars orbit each other extremely closely, whirling around their common center of mass in just hours or even minutes. These systems lose energy by radiating gravitational waves, ripples in spacetime itself, causing the orbit to gradually shrink. As the stars spiral closer together, they orbit faster and faster, the gravitational time dilation at their surfaces increasing, their clocks running slower and slower relative to distant observers. The Hulse-Taylor pulsar binary, discovered in 1974, provided the first indirect evidence for gravitational waves through exactly this effect. The two neutron stars orbit each other every 7.75 hours, and careful timing of the pulsar's radio pulses revealed that the orbital period is decreasing by about 76 microseconds per year, precisely matching the predictions of general relativity for energy loss through gravitational wave emission. Over the decades of observation, the orbital decay has matched Einstein's equations perfectly, a beautiful confirmation that spacetime can ripple and waves of gravity can propagate across the universe. In about 300 million years, these two neutron stars will spiral close enough to merge, colliding in a cataclysmic event that will release tremendous gravitational waves and likely produce a burst of gamma rays and heavy elements. Time will slow to extraordinary degrees at the surfaces of the stars in their final moments before collision, and when they finally touch, they may form a black hole, creating a new region where time behaves in even stranger ways. Let these thoughts of time dissolve now. Let go of clocks and schedules and the relentless forward march of moments. Here, in this space between waking and sleep, time becomes fluid, elastic, almost meaningless. You exist in an eternal now, where past and future blur together, where duration loses its grip. You've traveled so far now, through so many stellar landscapes, your consciousness like starlight itself, diffuse, gentle, spreading out into the darkness. Let's explore something deeply peaceful, the way stars sustain themselves through balance, through equilibrium, through forces held in perfect tension. A star exists in a state called hydrostatic equilibrium, a beautiful balance between two opposing forces. Gravity pulls inward, trying to collapse the star into an ever-denser sphere. Pressure from the hot gas inside pushes outward, resisting that collapse. For billions of years, these two forces remain perfectly matched, neither winning, neither losing, the star held in stable suspension like a soap bubble floating on air. This is not a static balance but a dynamic one, constantly adjusting, constantly responding, maintaining stability through continuous subtle changes. Our sun performs this balancing act every moment. The pressure at its core is approximately 250 billion times Earth's atmospheric pressure at sea level. That's 250 billion times the pressure you feel right now, pressing down from the weight of all the air above you. Under such immense pressure and temperature, hydrogen nuclei overcome their natural repulsion and fuse together, releasing energy that creates the outward pressure needed to balance gravity's inward pull. The Sun is, in essence, a controlled fusion explosion that has been ongoing for 4.6 billion years, held in check only by its own gravity. When this balance is disturbed, when a star exhausts its fuel or gains too much mass, dramatic changes occur. We've spoken of red giants and supernovae, but there's another transition worth contemplating, the moment when a star first achieves equilibrium and begins its stable life. Before fusion ignites, a protostar is not in equilibrium, it's still collapsing, still heating, still gathering mass. The moment fusion begins is the moment balance is achieved, when the inward and outward forces finally match, when the long stable period begins. It's a birth, a coming into being, the transition from becoming to being. Different stars find this balance at different sizes. The smallest stars that can sustain hydrogen fusion have about 0.08 times the mass of our Sun, roughly 80 times the mass of Jupiter. Below this threshold, objects can never achieve the core temperatures needed for fusion. These failed stars, called brown dwarfs, glow dimly from the heat of their formation, gradually cooling over time, never finding the balance that would make them true stars. Their stellar might have beens, objects caught between planets and stars, too massive to be one, too light to be the other. Brown dwarfs occupy a twilight realm. The largest can have surface temperatures around 2000 degrees Celsius when young, hot enough to glow a dull red. The coolest brown dwarfs we've discovered have surface temperatures below 100 degrees Celsius, cooler than boiling water, comparable to a hot summer day on Earth. These objects blur the boundary between star and planet, radiating in infrared wavelengths, barely visible even to sensitive telescopes. They drift through the galaxy in darkness, failed suns that never quite ignited, never quite found their light. And yet, even brown dwarfs have a kind of balance. They're supported by electron degeneracy pressure, the same quantum mechanical effect that holds up white dwarfs, preventing gravitational collapse without needing fusion. They find equilibrium at a different point, through different means, settling into stable configurations that will persist for trillions of years. Even in failure, even in falling short of becoming a star, they achieve a kind of peace, a stable state where they can endure essentially forever. At the other end of the mass spectrum, the most massive stars face a different challenge. Stars more than about 150 times the Sun's mass become unstable. The radiation pressure from their cores, the outward push from light itself, from photons produced in such abundance that they exert measurable force, becomes so strong that it nearly tears the star apart. These monsters exist right at the edge of stability, sometimes shedding vast amounts of mass through powerful stellar winds, sometimes pulsating or experiencing eruptions as they struggle to maintain equilibrium against their own luminosity. One such star, Eta Carinae, experienced a massive eruption in the 1840s, briefly becoming the second brightest star in Earth's night sky despite being 7,500 light-years away. The star expelled several solar masses of material in that outburst, creating the beautiful homunculus nebula that now surrounds it. Eta Carinae still exists in a precarious balance, one of the most massive and luminous stars known, burning so fiercely that its lifetime will be measured in mere millions of years before it ends in a supernova of extraordinary power. Balance, equilibrium, forces and tension, these are the themes that govern stellar existence. And perhaps they govern all existence. We too seek balance, between work and rest, between engagement and solitude, between the demands placed upon us and our own inner needs. Like stars, we're held together by invisible forces, pressure and gravity of different kinds, seeking that point of equilibrium where we can burn steadily, sustainably, for as long as we're meant to shine. Rest in that balance now, all tensions released, all pressures equalized, finding that perfect point of stillness where nothing needs to be done, nothing needs to change. We've come so far together, through billions of years and trillions of kilometers, through births and deaths and the quiet spaces in between. As we approach the end of our journey, let's return to where we began, to you, here, now, in this peaceful darkness, and to your connection with the stars above. Every atom of oxygen in your lungs was created inside a star at least twice as massive as our Sun, forged through nuclear fusion in its final stages of life. Every atom of calcium in your bones came from a star that ended in a supernova, its death scattering enriched material across light years of space. The iron in your blood, the sodium and potassium that allow your nerves to fire, the phosphorus in your DNA, all of these elements were created in stellar furnaces and distributed through the galaxy by stellar winds and explosive deaths. You are, quite literally, the universe becoming aware of itself. You are billions of years of cosmic evolution concentrated into a single awareness, a brief flowering of consciousness made possible by generations of stars that lived and died to create the elements you're made of. When you look up at the stars, you're not separate from them, not merely an observer, you're part of the same story, made of the same substance, connected by an unbroken chain of creation that stretches back to the beginning of time. The number of atoms in your body is approximately 7 times 10 superscript 2, 7 billion atoms, each one with its own history, its own journey through the cosmos. Some of those atoms may have been part of the original molecular cloud that formed our solar system. Others may have cycled through countless stars before arriving here. Still others may have drifted through interstellar space for billions of years before eventually finding their way to Earth, to you, to this moment. You are an assembly of cosmic travelers, a temporary gathering of ancient stardust. And this gathering is temporary, wonderfully, beautifully temporary. The atoms that make up your body will not stay together forever. Eventually, through the natural processes of life and death, they will return to the environment, be taken up by other organisms, cycle through ecosystems, perhaps eventually return to the earth or the sea or the air. Billions of years from now, when the sun becomes a red giant and Earth's story ends, the atoms that were once you will be scattered, perhaps ejected into space, perhaps incorporated into the stellar wind the dying sun produces, sent back out into the galaxy to begin new journeys, to become part of new stories we cannot imagine. Nothing is truly lost. Matter and energy persist, transform, continue. The carbon atoms in your body were once in dinosaurs, in ancient ferns, in the first single-celled organisms that arose in Earth's primordial oceans. Before that, they were in the molecular clouds between stars. Before that, they were inside dying stars, being forged in nuclear fire. And after you, they will continue, carrying forward into futures we cannot see, becoming parts of stories not yet written. There is comfort in this continuity, this endless recycling, this participation in something eternal. You are not separate from the cosmos but woven into it, part of its great tapestry, one thread among countless others, unique but connected, individual but part of the whole. The same forces that hold stars together, gravity, electromagnetism, the strong and weak nuclear forces, these are what hold you together, what make you possible, what allow you to exist and think and wonder about your place in all of this. The stars will outlast you, yes. Most of them, anyway. The sun will shine for 5 billion more years. The small red dwarfs will glow for trillions. But you, right now, are something the universe has created that most stars will never achieve: awareness, consciousness, the ability to contemplate existence itself. You are the universe's way of knowing itself, of experiencing itself, of wondering about its own nature. That makes you precious beyond measure, irreplaceable despite your temporary nature. So rest now, knowing you are home. You are made of stars, surrounded by stars, held in the embrace of a cosmos that created you from its own substance. You belong here, in this moment, in this place, in this vast and ancient universe that somehow, impossibly, gave rise to you. The stars are still there, beyond your closed eyes, beyond the walls and the daylight and the atmosphere. They're always there, constant companions on Earth's journey through space, fellow travelers in this cosmic dance. And tomorrow, or whenever you wake, they will still be there, waiting patiently, shining steadily, keeping their ancient watch over our small world. Sleep now, child of stars. Sleep deeply, peacefully, held in the gentle darkness that connects all things. Let your consciousness dissolve like morning mist, let your thoughts fade like distant starlight, let yourself drift into the vast, quiet peace that existed before the first stars ignited and will remain after the last one fades. The universe cradles you in its infinite arms. You are safe. You are home. You are, and have always been, made of light. Sleep well, stardust. Sleep well,